Hi, I'm excited to introduce our work, Frequency-Aware Self-Supervised Monocular Depth Estimation. The depth estimation network takes a single RGB image as input and outputs its pixel-aligned depth map. We begin with a quick review of the self-supervised monocular depth estimation training pipeline. The CNN model is composed of two networks. The DepthNet outputs the depth map of the target image IT, and the PoseNet takes two adjacent images as input and outputs the relative camera pose. Each pixel from target image is projected into source view to compute the sampler, which says for each pixel in IT, where is the corresponding pixel in IT plus n. Therefore, the reconstructed image can be generated by sampling from the source image. The final loss is formulated by the photometric distance between target image and reconstructed image. However, from the perspective of spatial frequency, we found the photometric loss cannot be a good supervisor to guide the depth network in some specific pixels or regions. We found some particular object boundary pixels are ambitious, which always produce irrational losses. Furthermore, we demonstrate that the photometric loss cannot fairly evaluate the depth prediction in high-frequency region. We start with the first problem. When training gets to the middle part, on most objects, loss only appear at the object boundaries. If the depth prediction is wrong, loss should have appeared on the whole object or a concentrated part. So where do these losses come from? If we enlarge the image patch multiple times, we can see the colors at object boundaries are the weighted summation of two adjacent objects. These colors are neither from the black roof or chimney, nor the white clouds. In fact, no real-world objects exhibit the weighted summation color of two different objects. Second is their locations. When projecting these pixels to 3D point clouds, they appear as noise outside the real objects, regardless of their predicted depth. To overcome this limit, we propose ambiguity masking. The ambiguity map pixel-wise multiply with the photometric error to simply filter out these ill pixels. And then we get the final loss. In particular, we first extract the ill pixels in target image and source image. Then, we bilinear sample AT plus n to get which pixel in the reconstructed image are from the ambitious pixel in the source image. We then take the pixel-wise maximum, because for each pixel in the loss map, ambiguity from either source image or reconstructed image can both cause its loss to be untrustworthy. Before introducing the second problem, we first define what is an absolutely fair loss. Given a loss function L with ground truth GT, for all x1 and 2 in a certain range, if x1 is more accurate, then the loss for x1 is smaller. This kind of loss function is regarded as absolutely fair. Take the loss function in one of the supervised depth estimation methods, for example, where it averages L1 distance between the predicted depth and ground truth depth over all n pixels. This is a typical absolutely fair loss, because the loss is proportional to the prediction error. We show problem 2 here. The loss function used in self-supervised depth estimation is the photometric loss as defined here. To demonstrate the problem, we focus on this pixel in left view. We aim to search where it appears in the right view. The losses for different predicted disparities look like this. If we consider these two disparities, the red one has the maximum photometric loss, while the orange has the minimum. However, the red one is closer to the ground truth, which means it's more accurate. This non-proportional relationship indicates that the photometric loss is unfair, because the poorer disparity instead has a smaller loss. What's worse, loss of ground truth is even larger than that of some incorrect disparity, which means the network has the wrong global optima. To alleviate this problem, we present auto-blur module. Augmented with auto-blur. As the yellow line shows, the photometric loss becomes more stable in high-frequency area. Most importantly, it becomes fair, in which the loss is proportional to the prediction error. Last but not the least, the loss of the wrong global optima gets increased, preventing it from deceiving the network. We then analyze how auto-blur works. Likewise, we aim to search where the target pixel in the left view appears in the right view. The middle plot shows the color intensities of different disparities in the right view, and the right plot shows the corresponding losses. We can see that all disparities share the same loss, regardless of their accuracy. Worse yet, when the assumption of photometric consistency breaks down, the mismatch may look more like the target pixel than GT with a smaller loss, thereby fooling the network. Augmented with auto-blur, the situation got changed. Under the action of Gaussian kernel, all pixels affect surroundings and are affected by surroundings. Our first benefit denotes the absolutely fair loss. The rule of auto-blur is to radiate GT's characteristic color, which means red, to the surroundings. Moreover, this radiation is inversely proportional to the distance, so that as the distance between predicted disparity and GT gets smaller, the photometric information of GT gets stronger, informing the network the current disparity is getting closer to GT. Therefore, within a certain range, our strategy can make the penalty on the network increase proportionally with the degree of network error. Our second benefit is to expose mismatch. Another effect of Gaussian kernel's radiation is to increase receptive field when measuring pixel similarity. The mismatch is radiated by surrounding blue, while the target pixel is radiated by surrounding green, thus making a difference. The loss of the mismatch therefore gets increased, preventing it from deceiving the network. So at this point, we have solved all problems mentioned before. Our methods are highly generalizable because the aforementioned problems we solved are fundamental and ubiquitous. We integrate our methods into a large number of existing open source models and achieve better results on almost all metrics, including those who claim to be state-of-the-art in their paper. Thanks for listening. Our source code and pre-trained models are all ready to be released.